Is it going? Okay, it's going. Okay, so they're supposed to be, I think, sending me like an extension cord for this webcam. Okay, so anyway, if they send me that extension cord, I'll be able to put the webcam over there and we'll get the board. So for now, luckily, we're working on something that it's actually going to be on here. So, okay, all right. We're just talking about that transformation thing. Number 5, number 6 would be what?
So, never mind. It's focusing in now. I just want to make sure you could actually see the screen.
Okay, thanks for checking it for me. Yeah, that's a tough part. It doesn't give me a little window down here of showing me what I'm doing, I don't think. So I have to like go back to my browser, and then it does this like infinite nesting. Okay, all right, maybe that. Okay, sorry if that's hard to see, but for now, it's the best I can do for now. George? All right. So, okay. Those are 2 points that live on the graph. I gave you 2 points for a reason instead of 1 point, because this is it's more of a nuanced effect, because look at, I guess we'll just show by example here what the effect is. So look at this guy here, absolute value of g of x. So can I still plug 6 in? Yeah, if I plug in 6, it's g of 6. Well, what's g of 6? -2. But what happens to that y value? It's turned positive. So the moral of that story is, if what this does to a graph is, if the y value is negative, it gets turned positive. Okay? But this is where it gets maybe a little interesting, is -3, 8. So can I still plug in -3? It's -3. But I still get 8. So if we summarize this, it would be, if the y value is negative, it gets turned positive. But if the y value was already positive, it stays positive. Or I guess you could summarize that as, you take the absolute value of every y value. But notice the x values, does it matter if the x was negative or positive? No. Nope, there was no effect. So next, for this is probably the more confusing one too. Can I still plug in 6?
Yes.
If I plug a 6 in there for the x, it says g of absolute value of 6, but absolute value of 6 is 6, so g of 6 is. So it always confuses people. They go, wait a second, what? It's still negative. Yeah, because it's the x value. Next, this is the really confusing one. If I were to plug in -3, it would read g of the absolute value of -3, but then that would be g of 3. What's g of 3?
We don't know.
We have no idea. So that's actually obliterated information. It's gone. What we do know is that if I plugged in -6 for my x, it would read g of 6, which is -2. So this is a really weird one. What this does is any point that had a positive x value is basically copied over to the left-hand side. It's mirrored over, reflected over the y-axis. And then any point that had a negative x value is just erased. Okay, so visually, we'll do some visually, but what that means is, if the graph, whatever, looked like this, then all of this stuff would just get erased. And then the new graph, all of these points would stay where they were, and they would get copied over to the left-hand side. So it looks like something like that. Okay. All right. Same thing for, 7's the same kind of question. All right. We'll just do one of these, like kind of one page of them, and then maybe let's do this one instead. I kind of like some better as an example. Okay, so then we're going to start off with the absolute value. Just get those out of the way. So, you got a wondering if with the camera here, I should stand over here. But hopefully it's visible. Okay, so taking the absolute value of the function, what's going to happen? Any point that has a positive y value is unaffected, so these guys are unaffected. But then any point that had a negative y value is now going to have a positive y value, so it's going to look something like that. So something to keep in mind, did we affect the domain? No. Did we affect the range? Yes. This guy, like we just talked about a second ago, all points that have positive x values, that's not very good job, is it? All the points that have positive x values are unaffected, and they're also copied over and overwrite all the points that had, close enough. That's a pretty weird one, right? This went from having a domain of negative infinity to 2, and now the domain is just negative 2 to 2. Same with the range. The range went from negative 3 to infinity, and now the range is just negative 3 to 1. So this one can have really drastic effects on the domain and range simultaneously. Let's maybe just gloss over these, because I think hopefully we've established what happened here. Shifted up 1. Shifted left 1.
Reflect over.
Whoop. Yep. Reflect over the y-axis. Okay. So imagine this one. Just go point for point. If you can't do it all at once, I mean, I probably can't either. Just I would say that okay, that point would move there, right? That point would move there. That point would move here, and the arrow goes here. So you're going to end up with something like this for f of negative x. So reflection over the y-axis. What does that one do? This is going to multiply all the y values by 1/2. It's going to shrink it vertically. It's going to be a vertical crunch. So point by point, it would just go x value is unaffected. So that little dot on that graph used to be at 2, -3. Now it's at 2, -1.5. That little hump in the middle used to be at 1. Now it's at 1/2. What is unaffected by this transformation? What type of points stay where they are? Anywhere where the
Y
yeah, anywhere where the y value is 0 or the x-intercept. Yeah, that's a good answer. X-intercept, so this x-intercept of 1 would be unaffected. And then notice what happens to this slope here. The slope used to be 1, now the slope's going to be 1/2. Unless, did I helps to have one with me.
Who's the
I do have one extra. Slop. Yep, so the slop used to be -1, now it's -1. What happens here? Reflects over the x-axis. Every point just multiply the y value by -1, and then lastly, this one we just talked about a few minutes ago. And so this point down here, instead of being at 2, -3, it's now at
2 negatives.
now remember. So going back to
Oh, it's 1.
exactly. So we know that f of 2 is -3. So what do we have to choose for our x value here to get that information to emerge? Well, I'd have to pick x value of 1, and then it would read f of 2 equals 3, or -3. So that point that used to be at 2, -3 is now at 1, -3. So now what kind of point would be unaffected by this transformation? The y-intercept. Very good, Alyssa. Good job. Good answer. So now it's going to be steeper. X values are affected. And then where was that one point before? It was at -3, 2. So now it's at -1.5. That's really Does that make sense? You okay with that? Oakley dokley. All right, so I'll just leave. I don't know. I feel like I don't need to like lecture on the other ones, right? We got the idea. So we'll also hopefully have a little bit of class time, maybe a little bit of work outside of class just to knock those out. 11 includes some problems that I find very interesting. So you might recall that I've mentioned before that calculus, one of the things we like to study in calculus is the pointiness of graphs. Where is that graph pointy? Where is he not? Where's his Humpty Dumptys? Things like that. And so this kind of thing, you're going to see a lot of these have little pointy spots in them. So, these would be kind of like, because what you're going to find is it's very difficult to apply calculus techniques to functions that have absolute values in them. But if you understand the graphs, you can make inferences about the functions by just like kind of thinking about how the graphs look. So anyway, sketch a graph of each function. You guys tell me, does this hint make any sense? I've had feedback in the past that hint makes no sense, but I've edited it before. No, Lillian? Are you saying it doesn't make sense, or? I think it used to say something like construct a function g of x and then think about how f of x is g of absolute value of x or something like that. And people say that doesn't really make sense. So I try to phrase it in more simple language. But so what I'm trying to say is, what do you think would be like the parent function here? The square root function. So you say, well, if I start with the square root function, then what's it going to look like? Here, see if you know the answer to this one. If this is a function, are we replacing the x with absolute value of x, or are we taking the absolute value of the function? We're replacing the absolute value. So what does that do? Yeah, we get that reflection, exactly. So we get.
It's a birdie.
You get, yeah, this is one way to get a birdie function. So it's a little, it's kind of interesting because, you end up seeing how it is structurally the same as like an x to the 2/3 power. When it is, because the absolute value gives you that, it expands the domain to allow negative numbers, which is what this has. Okay, so you get a birdie there. Great. Let's try this one. The parent, I forgot to make here. I'll draw the parent function really tiny up here. The parent function would be a simple exponential decay graph. So it would look like this. Everyone okay with that? Now take that and then apply the f of absolute value of x transformation to that. What's it going to look like?
It's gonna.
Okay. I'm very hesitant. I mean, I get what you're saying with the birdie thing, but I would say this is not a birdie because this birdie, there's no upper bound. His range is 0 to infinity, whereas this guy's a very fascinating range. You're constrained from 0 to 1, which is pretty interesting. So an infinite number of x values. So to say their similarities, they both have a domain of all reals, but this guy actually is really constrained in this narrow band. So well, it's very interesting because it shows one way. What?
Look at this narrow infinite band.
Very constrained.
It is, yeah. Well, if any of you guys end up being math majors, they'll take a class called analysis where you talk about how, because you might say, what are there more of, real numbers or numbers between 0 and 1? And it's the same amount. And you can, to prove that, you show how there are functions that map, say, all the real numbers and shrink them down to this narrow little band. But anyway, so the arctangent function is another one that does that pretty easily. So, alrighty. C. This one's a little weird. We have two options here, I think. You could, I think it's really cool, you can look at the two different ways to look at this. One, so I'm gonna use up kind of all the space here, but you can choose which one you wanna go with it. Say you started off with, kind of want to throw this out and let you kind of think about it for a second. What if you started off with this? What if you said your parent function was absolute value of x minus 2? How would you think about this function? Alternatively, what if you started off with thinking about it as the absolute value of x minus 2? I guess I hope I don't confuse anyone by doing it both ways here, but do you see how you could do it either way? You could start with this and say, you know what I'm doing? I am,
It was just like,
for this one, I'm actually putting absolute value around the function, which means I take this and I take all the y values that are negative and I make them positive. So that's one way to go about it. So that's one where you say I'm starting with this, and then I'm putting the absolute value around the function. And then this one, though, from this perspective, now it's math, so you know it's going to be the same answer, or else our entire system breaks down. But in this one, I'm actually replacing the x inside the function with an absolute value of x. So now I do that other thing where I say, well, I keep all the positive x values stay the same, and then I copy them over to the left-hand side. Isn't that neato? That's pretty neato burrito, if you ask me. Two more. All right. This one.
Those are my least favorite letters.
What's your least favorite letter?
C.
Oh, I skipped one. Sorry, I skipped one. My bad.
No, like of the letters of the alphabet, my least favorite letter is C.
What's your favorite?
T.
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 Why? Because your name's Trenton.
Yeah.
Or what's your favorite letter?
Don't have
J.
Don't have one.
Yeah, J. It's J.
M for math. Okay, so anyway, I love this pair of questions here because they look pretty similar, right? They're very close, but we got pretty different answers here. So I don't know, am I out of line to say that this one it's obvious that once you know the function, the absolute value bars are going around the outside of the function. This is basically one of those f turning into absolute value bar. Now, do we remember how to graph this by itself? Let's think about that. That's one way to do it, yes, to factor it. So you'd say, how do I graph? I know it's a parabola. We all know that, hopefully. Factor out the x, and now it's a little bit more obvious what it looks like. It's a parabola with zeros at 0 and 2. We all okay with that? So that's my parent function now. And so what do I do? Now we put absolute value bars around it. So can you picture it in your head? You see it? It's like that. Another kind of W-like shape. How are we doing for time here? 10?
This one's
There's still more things. All right, now in the old brain, can you already see what this looks like, or no? And I'll give you a hint if you're kind of like, what? Is this like some sort of trick? It's not. I will point out that this is equivalent to this. Right, because squaring makes things positive anyway. Yeah. So now that maybe if that wasn't occurring to you, now do you see how it's the same parent function, but we're applying now the replace every x with absolute value of x transformation? So does anyone remember the mathematician that discovered this one?
I think you did tell us.
I think I told you, yeah, it's pretty famous.
No, J Hall, it's no, just wrong. I'm not gonna fall for this.
Jesse. Wilford P. Butts. Oh, high level humor. That's very high level, guys.
Very.
It's very.
If you're not laughing, you just don't understand.
It's too intellectual. It's too intellectual of humor. But you get how we're getting from that parabola to that transformation, copies that info, copies the positive x value points over. All right, so. All right, one more. This guy here, this is another interesting one because, again, I'd say it's pretty obvious what's happening here. You're taking a function, you put absolute value bars on it. So we got to first ask ourselves, what does it look like if you go, what does it look like to go 1 minus 1 over x squared? So it's a good mental exercise. Start with this,
Yeah.
and then two things happen to him.
Goes up one, yeah.
He flipped, and then shifted up. So it looks something like this. Is everyone okay with that?
Yeah.
Now we put the absolute value bars on the outside, so these little negative pieces here are going to flip up to the top, and so the graph looks. It's another good example of a function. Now it's kind of convoluted, but one where you cross the horizontal asymptotes. Kind of a strange looking function, right? So it has a vertical asymptote at 0 still. It comes down, bounces pointily off the x-axis at 1, -1, and then goes off.
That's the
to
letter O.
Alrighty.
That's one of the reasons
Is
it's
this
on
the
this.
funkiness you're talking about?
Yeah, so this is one where soon we'll have something called the derivative, and we'll say, oh, there's pointy here, so the derivative is non-existent at these two. Also at 0, but
There's a good list of those.
okay. This one is one that. So, sorry if I ruined your fun by going over all those answers, but I wanted to make sure we understood that one pretty good. 12 and 13 and 14 and 15. Really, the rest of it, I'll briefly cover piecewise functions tomorrow, but tomorrow you'll have some time in class to look at the practice quiz. This one, I mean, correct me if I'm wrong, but I think these should be fairly easy. I'll briefly go over like the notation just to review, but I don't think you guys are going to need me to like show you many of these. Like f of h of 4. So what do? You plug 4 into h. You'd get 12 minus 5 is 7. And then 7 goes into f. So what's the answer here? Root 10. You okay with that? So f is this some notation? K over f of 1. That's just a different way of writing k of 1 over f of 1. So what do? You plug 1 into k, -6. You plug 1 into f. So the answer is -3. Makes sense? So that just means divide. That means add. The little dot means of. So this is a different way of writing g of k of 6. That little O means of. We can definitely check some answers tomorrow, but I'd like you to take 10 minutes and kind of knock these out on your own. Pay special attention to 13 and 14. because it would be easy to make a mistake of going, oh, f of g and g of f are the same. They are not the same. They have different domains. Okay. And for 15, it's just use the graphs to figure them out. We can go in. So I don't know. For homework, just try to finish through 14. How about that? Tomorrow we'll knock out the last one.